Hi guys, this is a review of the notes that I gave in class on Thursday the 16th of April. And this was a discussion of ionic bonding, which was one of the two ways that we're going to talk about how atoms actually bond with one another. In this type of bond, you have a transfer of electrons. So what I've drawn here is what it looks like when it's all done, and what the balance of charge is in both the atom and the ion. So these are the notes that were up on the board, but let me break it down for you step by step on a fresh page. So I have two atoms here, sodium and chlorine, and neither one of them is particularly stable because they both have incomplete valence shells. If I draw their Lewis structures, or their dot diagrams, this is what they look like. They look like this. So sodium has one valence electron, chlorine has 7, and neither one of them is completely stable. Sodium, in fact, is very, very unstable because he needs 8 to be full. So how can sodium get 8 electrons? Well, in theory, he could grab 7 electrons from somebody else, but that takes a lot of work and effort. It would be a lot easier for him to just boot out that electron that's in his valence shell. And he would do that because underneath, inside, he actually has a full valence shell just below that. Here's the nucleus of the sodium atom. It has 11 protons and 12 neutrons. Protons are positively charged, so those protons have attracted 11 electrons, 2 in the first shell, 8 in the middle shell, and 1 in the outer shell. So you can see that if that outer shell vanishes, sodium has a full shell just underneath. You see that? Here's the full shell underneath. 1, 2, 3, 4, 5, 6, 7, 8. So therefore, what sodium will do is if there's a source of positive charge somewhere else, somewhere nearby, it'll boot that electron out and let it go to that other positive charge. Conveniently, chlorine has 17 protons positively charged, and 18 electrons are attracted to that. 2 in the inside shell, 8 in the middle, and 7 in the outer shell. So, this positive charge in the nucleus of chlorine is enough pull to grab this electron and pull it over to here. When that happens, both sodium and chlorine will have full shells. Sodium's new valence shell is in here, and chlorine's is here. That's the basic idea behind ionic bonding. It's a transfer of electrons from a metal to a nonmetal. Sort of by definition, you're a metal if you can give away electrons. And the only atoms that can give away electrons are atoms that have fewer than 4. Because, well, 4 or fewer. And that's because it's easier to give away 3, 2, or 1 electrons than it is to find 5, 6, or 7 electrons. So you'll get ionic bonds between things that are on the left-hand side of the periodic table and things that are on the right-hand side. When we draw them, they look like the notes that I showed you on that first slide. Let's look at this complicated set of notes from the top. Up on the top left-hand side, you have sodium drawn as a dot diagram, as an atom. After he gives away that electron, we draw him as an ion. An ion is an atom that has a charge, and what sodium does is he gives away that electron, his new valence shell is full, so he'll have 8 electrons around him, and we offset him with those squarish looking brackets just to make sure that when you're looking at that on paper, it immediately occurs to you that it's an ion. Now, you can see down at the bottom, if I were to draw the Bohr model for the sodium ion, it looks similar, but I would just include the protons and neutrons and the electrons that are on the inside shell. And now you can see down at the bottom where I have the word sodium here. Ooh, always doing that every time. There's the word sodium. I'm comparing the balance of charge in the atom to the ion. So in the atom, you have 11 positively charged protons and 11 negatively charged electrons, and that gives you a net charge of 0 because they balance each other out. All atoms are electrically neutral. They don't have a charge on them at all in their normal atomic state. However, once sodium gives away his electron, he's now going to change the balance of charge. So we're going to get 11 positively charged 11 positively charged protons in the nucleus of sodium. They stay put. They don't do anything. But we've lost an electron, so now we only have 10 negative things. So the net charge is 1 positive. And that's why all ions should have a number with a plus sign next to them or a number with a minus sign next to them. Chlorine gained the electron, so its new dot diagram as an ion looks like that. So he's got the bracket, he's got a full shell, and he has a charge of 1 minus because look down here. He had 17 positively charged things and 17 negatively charged things, which gave him a net charge of 0. Now he has 17 positive things, but 1 extra negative thing, giving him a net charge of 1 minus. Let's say that I want to bond 2 different atoms. I've got magnesium and chlorine, and the question is, how will they look when they're bonded to each other using the dot diagram method of drawing bonds? Well, the first thing you want to do is always ask yourself, do I have a metal? Because if you don't have a metal, you can't draw an ionic bond. And in this case, I do. I have magnesium, which is a metal. So the dot diagram for magnesium is just 2 dots on top because magnesium has 2 valence electrons. And as we've said before, chlorine has 7. But the next step is actually we need to figure out whether or not this bond is going to happen with just 1 magnesium atom and 1 chlorine atom. You've probably noticed that there are chemical formulas that have little subscripts, 2s and 3s and 4s, down at the bottoms under the numbers. Like in H2O, there's a little 2 down at the bottom. That's because atoms don't have to bond 1 to 1. Sometimes they bond 2 to 1 or 1 to 2 or any combination you can think of. So the question here is, what works in this situation? Well, magnesium can give 1 electron to chlorine, and that will help chlorine become full. But it won't help magnesium because he'll still have an extra electron on the outside shell, and he's going to need to get rid of that one also. So what we need is another chlorine atom. We need a second chlorine to give the second valence electron in magnesium to. This is work that you're going to want to do either on scrap paper or in your head, figuring out how many of each atom you're going to need. After you've done that, you can go ahead and start writing the bond, because this is what I now know. I know I need 1 magnesium atom, and that magnesium starts by looking like that. And I'm going to add it to, I'm going to chemically react it with 2 chlorine atoms, and I know that chlorines have 7 valence electrons, like that. After the chemical reaction occurs, I'm going to get the compound, magnesium chloride, but I have to remember to put that little 2 down there, right? Now, that is the formula for it, but that's not what I want to write here. I'm drawing the bond. So instead, here's what I do. You want to redraw magnesium as an ion. To do that, you're going to show him with a bracket around himself, pardon the bell, and I'm going to add in the valence electrons, because now he has a full shell underneath, and the charge that magnesium has. Now think about this. He gave away 2 electrons. That's going to mean he's going to have a charge of 2 plus, not 1 plus. Then I have to do the chlorines. I know I have 2 of them. Notice how I don't write the plus sign on this side, because now they're bonded to each other. They're not being added to each other. They're actually stuck together. The chlorine is going to look like this. Full shell, because that was the whole point. And he's going to have a charge of -1. Now you might say, well, how come not -2 or 2 minus? Well, that's because I have 2 chlorines. Each one of them gained an electron, so each chlorine has a -1 charge. That's how you draw an ionic bond, and we're going to practice it quite a bit in class, and I'll see you there.